Hi class, in this lecture we want to talk about part 3 of chapter 17, which talks about the death of high mass stars, and we're initially including in this definition of high mass what we really call intermediate mass stars. So right now anything that's greater than 2 times the mass of the sun is what we'll talk about, and then we'll split off from those intermediate mass stars to the really high mass stars greater than 8 times the mass of the sun and see what the differences are there. So here's a HR diagram really quick of what's going on for the really massive stars, and we'll talk about why this is happening. But the really massive stars will of course get bigger and cooler at the very surface, but hotter in the core, as we talked about for the lower mass stars. And so there's this kind of zigzagging back and forth in the HR diagram as the stars die. But the luminosity, it turns out, stays fairly constant. So remember that luminosity is this vertical axis on here. And as the really massive stars die, their changes in outer temperature and size are such that the luminosity remains fairly constant. The energy produced remains relatively constant, but it gets produced in a different way, and it gets kind of produced faster and faster and faster as it dies. So the fuel gets run out very quickly, gets depleted very quickly. So this is a 9 solar mass star, 25 solar mass star, 40, 85, and so on. And we'll talk about how these deaths of these stars progress at a much faster rate for the higher the mass. The higher the mass, the faster things happen, the much shorter the lifetime is of the star. So in these high mass stars, the temperatures are much greater, or can be much greater than the low mass stars. And so not only do you have the proton-proton chain producing helium from hydrogen, but you also have another process called the CNO cycle. And the CNO cycle uses carbon that's already present in the star. The stars all these stars, even the low mass stars, have carbon in them to some degree. Unless you were one of the very first stars ever made in the universe, you wouldn't have any carbon. But because other stars produced carbon, they died, they scattered that carbon throughout the universe. New stars were formed out of that material. Every star that's been formed that isn't an original star in the universe has some carbon in it. And so the carbon can actually be used as a catalyst to convert hydrogen into helium. And so this cycle is a little bit complicated. It's not terrible, but the first step is that a hydrogen will come along and hit a carbon-12. And when the hydrogen hits a carbon-12, of course the hydrogen is a proton, positively charged. The carbon-12 has a bunch of protons in it, and so it's got 6 in there. You can't see them all. So there's a much bigger repulsion between these particles because they both have positive charge. So it takes more energy to do this, to squeeze them together. But it can happen in the higher mass stars more easily than it can happen in the low mass stars. And so if you have a hydrogen hitting a carbon, you can get light coming out, and you get a nitrogen. You get a nitrogen atom. This is a proton combining with 6 protons. You get something that has 7 protons. But some light comes out, some energy is lost in the process. This nitrogen floats around in the nucleus, or in the core of the star, and eventually it decays. It just kind of spontaneously turns into a carbon-13. That's a carbon with 6 protons but 7 neutrons. So a proton in the nitrogen actually gets converted into a neutron. And in the process, a neutrino comes out, very weakly interacting particle comes out, and a positron, an anti-electron, comes out as well. And those particles go off and fly through the sun. The neutrinos pretty much just leave, not the sun, but the star. The neutrinos pretty much just leave and head out somewhere. The positron may then encounter an electron and annihilate the electron and produce energy there. So that's another way of producing energy, very similar to what happens in the proton-proton chain. Once this nitrogen decays, forms this carbon-13, that carbon-13 could encounter another hydrogen. And again, this carbon-13 just is kind of wandering around in the core. It might encounter another hydrogen. They combine, they produce light, they turn into a nitrogen again, but it's a different nitrogen than what we had before. It's a nitrogen-14 instead of a nitrogen-13. So that nitrogen-14 is a more stable nitrogen, and it just kind of hangs around, and it might encounter another hydrogen. That hydrogen will combine with it, proton will combine with it, form an oxygen-15. That oxygen-15 is unstable, and so it'll eventually decay. But during this process of the nitrogen-14 colliding with the proton, energy is released. When the oxygen decays, more energy is released in the form, though, of another neutrino and a positron. That positron can then go and annihilate an electron and produce more light. this nitrogen-15 ultimately then encounters another hydrogen that breaks it into a bigger piece, this helium now, and then we get back to carbon-12. So in this entire process, we start with a carbon-12, we end with a carbon-12, but there's these intermediate steps in between, and what comes out is the same stuff that comes out in the proton-proton chain. We have some gamma rays here and here and here. We have some neutrinos and positrons there and there. It's the same amount of stuff that comes out as what we had in the proton-proton chain. So it produces the same amount of energy. It enables stars that have higher temperature to produce this energy in more than just one way. Instead of just the proton-proton chain, you have this other possible cycle as well. So these more massive stars that can have higher temperatures can produce energy, can use the hydrogen much faster because there are more processes available to it. So the energy gets used much faster, not only because the temperature is higher and things are moving around faster and colliding more frequently, but because there's multiple processes taking place at the same time. So a lot of radiation pressure can be exerted then. A lot of energy is being produced. A lot of radiation pressure is pushing outward against the outer layers of the star. So these massive stars can have really incredibly strong solar winds, and they can be losing mass continuously. They can lose thousands of kilograms. They can lose an amount equal to the sun in about 100,000 years. And 100,000 years is not a lot of time when you think about the lifetime of a star. So think about a big massive star losing a whole solar mass worth of material because of this intense solar wind over just 100,000 years of its lifetime. It's a lot of material being spewed out from this very energetic star. So then what happens in the later life stages of these stars? So what we were just talking about was just the main sequence. Those are just stars, massive stars turning hydrogen into helium. They're still in the main sequence. So now what happens as they start to run out of hydrogen in their core? So these massive stars burn this hydrogen very quickly. So they may only last a few million years in total on the main sequence. But the normal kinds of things start happening. The hydrogen is converted into helium. The helium is left behind in the core and just kind of sits there for a little bit. As the core becomes an inert ball of helium, we get hydrogen burning in a shell. When we get that hydrogen burning in a shell, the core is contracting, but the energy produced in that shell can be greater, and that can push the outer layers of the star outward even further, and you get what we call a supergiant. We get not just a giant star, but it's a supergiant star because it's a much more massive, much bigger star already to begin with. It becomes even a bigger giant star than what we had before with our low mass stars. And then eventually we can have the helium in the core start to fuse. We don't get a helium flash in the case of these intermediate and high mass stars because the thermal pressures remains great enough to push against gravity. Degeneracy pressure doesn't become a factor here. And so once the temperature gets high enough, nuclear fusion of helium begins in the core, and the core then expands right away, and then the shells around it, that hydrogen burning shell around it, expands a little bit and cools a little bit. The total energy output decreases a little bit. The outer layers actually contract a little bit, and so the star gets a little bit smaller, but it's still a supergiant. It doesn't go back to the size it had on the main sequence, but it might be a little bit smaller. So like we saw with the low mass stars, we have these kind of zigzagging, and we'll look at this again, the sort of zigzagging on the HR diagram of these stars as they expand and contract. So very similar things are happening inside of these very massive stars as what was happening inside of the low mass stars initially as they start to die. There's just no helium flash. That's the main difference. So the helium core fusion leaves behind an inert ball of carbon now. So helium fusion produces carbon. And that ball of carbon in the core just kind of sits there. As the carbon accumulates, gravity squeezes it and it shrinks. The temperature has to get hot enough that eventually for that carbon to be fused together to form other things. And so here's where we distinguish between intermediate stars and the high mass stars. If you are a star between 2 and 8 solar masses, your temperature won't get hot enough to burn carbon into anything. And so eventually that carbon ball will be just a carbon ball, a very hot carbon ball, supported by degeneracy pressure, electron degeneracy pressure. And the outer layers, and you'll have you'll have two shells of hydrogen and helium burning around the carbon core. and those shells will be unstable. They'll be sort of increasing and decreasing energy output a little bit erratically, causing these sort of pulsations like we talked about with the low mass stars. And eventually the outer layers will get blown away, and you'll have a planetary nebula, and you'll be left with a ball of carbon, a white dwarf carbon ball, left behind to cool for a very, very, very long time. So the intermediate mass stars will end up kind of similar as the low mass stars. They'll end up as a white dwarf, carbon white dwarf, and they'll end up as a planetary nebula. You won't get a massive explosion, as what we'll talk about with the high mass stars. So what about the high mass stars then? So thinking about what they're going to produce, let's go back and remember that in the Big Bang produced about 75% of all the material that the Big Bang produced. 75% of it was hydrogen, about 25% helium, and maybe just a trace amount of other things like lithium. So here's lithium right here, element number 3. So hydrogen and helium were produced in the Big Bang itself. And then we know that inside stars, helium fusion can make carbon. And this can happen in all stars. This happens in every single star. It happens in low mass stars. Possibly the very lowest mass stars, though, might only produce helium. So we talked about how the very low mass stars ultimately produce helium white dwarfs. They can't even get carbon. But most stars produce carbon. And then the CNO cycle can change some of that carbon into nitrogen and oxygen. So we can get some nitrogen and oxygen produced in that process, the CNO cycle inside of the cores of the stars. And then there's another process that can occur. As the temperature gets higher and higher, more things can happen. So in the higher mass stars, where there's enough temperature, you can actually start taking some of those heliums you've produced, combining them with carbons to get oxygens. You could also take those heliums that you've produced, combine them with those oxygens, and produce neons. Or you can take those heliums that you've produced and combine them with those neons now that you have and produce magnesium. So there's different processes that you can go through, and the bigger the nucleus, the more protons there are in the nucleus, the more energy you need for this process to occur. The faster these guys have to be moving so they get close enough to fuse together to form this bigger thing. So there's these various what we call helium capture processes that can occur, and they all require much higher temperatures than what you get in the low mass stars. Some of these processes could occur in the intermediate mass stars, but not much. Again, it takes a very high temperature even to fuse a helium into a carbon. So you might get some of this oxygen produced in the intermediate mass stars, but you probably won't get very much of the neon produced because it requires even more energy. And you certainly, in the intermediate mass stars, you certainly can't take a big old carbon and collide it with another carbon. There just is not enough energy available. These things are not moving fast enough to get close enough together. So this helium capture process is a way by which we can make bigger elements, and it happens primarily in the high mass stars, the highest mass stars. So here we add to our periodic table magnesium, carbon, oxygen, neon. We already had carbon being produced by helium fusion, but we can get it we can get the carbon then producing oxygen, and then oxygen produces neon, and neon produces magnesium, and so on. And then there's other processes, and again, these will occur only in the highest mass stars, greater than 8 solar masses. So if you're greater than 8 solar masses, then you have enough energy, or you'll eventually have enough energy, enough temperature, to be able to take a carbon and fuse it with an oxygen to form silicon. Or take an oxygen, fuse it with another oxygen to form sulfur. Or take a silicon, fuse it with another silicon to make iron. So you can make these much, much more massive nuclei, but this only happens in the most massive stars, 8 solar masses or above. So now we have our periodic table, we have more elements that we've added. So this is ultimately where all these elements come from, is in the cores of these stars. And you see, we still have a lot of missing things. We've discovered all these other elements, but so far there's all these other things in here that we haven't really accounted for. So in the kind of a rough model of then what's going on in the most massive stars is you get this sequence of core burning, and then the core stops burning, and a shell of whatever was burning starts around the core. That core shrinks and eventually gets hot enough to then burn the next thing. And so ultimately you get this iron core in the very center. Once iron is being produced in the core, it just sits there and it doesn't do anything. And you get around it, you get silicon burning, silicon fusing with silicon to produce the iron. Around that you have a shell of oxygen, neon, magnesium doing various things. Around that you might have a shell of carbon fusing into things like oxygen, magnesium, and neon. Around that you have helium fusing into carbon. Around that you have hydrogen fusing into helium. So as you get the core, as the core is fusing something, you've got these shells like an onion, layers like an onion around the core, fusing different things. So you have all these different fusions going on. A lot of energy is being produced. And every one of these steps goes faster and faster and faster. Every time a core fusion stops, fusion in the shells intensifies, becomes stronger. The core then shrinks and the outer layers expand. And then as fusion begins again in the core actually expands a little bit, cools the shells down a little bit, and the outer layers actually then contract. The gravity can squeeze a little bit. So there's always this sort of opposite thing. As the core expands, the outer layers contract, or as the core shrinks, the outer layers expand because of the way that energy is being produced. But ultimately, iron is the last thing that a star can make. And we'll talk about that in just a second. So there's a lot of changes going on inside these big stars. And so they kind of zigzag back and forth on the HR diagram, but their luminosity remains relatively constant. But there's this sort of zigzagging back and forth as the size of the star is changing, as the outer layers are cooling and warming up and so on. And these changes happen very fast, and they happen very, very fast for the highest mass stars. They happen so fast for the highest mass stars that you almost can't even tell that there are any changes occurring when you just look at the surface, the outer surface. Things just happen so fast that the outer surface remains relatively constant. The temperature just gradually, on the very outer surface, gradually decreases. So iron is the dead end. Iron is the end of the line for fusion. You can't take iron and squeeze it together and get energy out. In order to fuse iron, you have to provide energy. You don't get energy out. So it's not going to happen naturally in nature. It's not going to happen inside these stars. One way to think about this is to think about what's called the amount of mass per nuclear particle. And if we think about Einstein's equation, E equals mc squared, we get energy from nuclear fusion by converting mass into energy. And so if we have a lot of mass per nuclear particle, we can get some energy out of it. Well, iron has the lowest mass per nuclear particle, so we can't get any energy out of it. And so what this means is if you take the mass of a nucleus, take whatever the mass is, take the mass of the nucleus, and you divide that by the number of particles in the nucleus. That's what this vertical axis is. It's the mass per nuclear particle. And iron has the lowest. There's no mass energy available to give something that's got less energy. So we want to get energy out. So for example, if we take hydrogen and we convert it into helium, hydrogen itself is just a proton. There's a certain amount of mass there of that one particle. Helium has 2 protons and 2 neutrons. So if we take the total mass of helium and divide it by 4, that gives us the mass per particle of helium. And we find that that's smaller. So we have lost mass in the process of taking 4 hydrogens and converting them into a helium. We have lost mass. That mass goes into energy. That's how we get our energy. Well, we can't do that with iron. We take iron and fuse it with itself. We don't get anything that has less mass. We can't get energy out. So if you're going to do fusion, the biggest nucleus you can get is iron. So what we do then in nuclear power plants is we actually do the opposite process. We do fission. And so we take uranium or other things, and these uraniums will naturally decay, and they will break up into smaller particles, like lead, for example. In that process, energy is released because when uranium decays, it produces particles, nuclei that have less mass per particle. So we've lost mass again, and energy is produced. So iron is the most tightly bound nucleus. We just can't do anything with it. It's the end of the road for stars. So that iron core is just going to keep contracting until perhaps degeneracy pressure supports it or makes it stop contracting. So we'll talk about what then happens when that iron core does something. What's the last thing that it can do? We'll talk about that in a minute. But how do we know that our models are correct? So what we can look at are, again, clusters of stars, and we can see, we know that in a cluster, all the stars were born at about the same time. And so when we look at the oldest stars in the clusters, we would expect them, or we look at the oldest clusters that we can find, the oldest clusters. We would expect them to have stars that have less of the heavy elements, a lower percentage of heavy elements. If you could find a star or a cluster of stars that was formed, let's say 10 billion years ago, it should have less, let's say, magnesium and oxygen and so on, than a star that was formed like 5 billion years ago. And that's indeed what we find. We find that elements heavier than hydrogen and helium make up only about maybe 0.1% of the total mass of the oldest stars in star clusters. And so astronomers take a lot of time looking at star clusters and really trying to find the really oldest star clusters and measuring what they call the chemical abundances of star clusters, atomic abundances, to see what is it made of. And if you find something that's primarily hydrogen and helium and almost nothing else, you know that that's a pretty old object. And if you look at things that are younger, much more recently created, you find that the heavier elements make up a much higher percentage of their mass, by between 2 and 3%. And so that's evidence that these elements, these heavy elements, are created in these stars. As stars are born and they live their lives, they create these elements, they then die in some way, and they spread the elements out into space for the next generation of stars to be born from. Evidence for helium capture, when we look at that helium capture process, again, helium has 2 protons and 2 neutrons, so there's 4 particles there. And what we find is that we do find a higher abundance of particles that have even numbered protons. So the helium comes along and it adds 2 more protons to a nucleus that it collides with. And we do in fact find that there are greater numbers of those atoms out in nature that have even numbers of protons. And so that's evidence for this helium capture process being something that's going on inside these stars. So how do these stars ultimately die? How do these big stars ultimately die? The highest mass stars. The intermediate mass stars, again, we said stars less than 8 solar masses. We said they're going to die and give off a planetary nebula and be left with a carbon white dwarf. And so kind of a somewhat benign process. But it'll do bad things for us here on Earth. But it's not an explosion anything like what happens to the highest mass stars. So iron builds up in the core until electron degeneracy pressure can resist gravity. But if gravity can squeeze high enough, strong enough, which it can in the highest mass stars, in a fraction of a second, gravity can squeeze that core so tightly that the electrons actually convert into, they combine with the protons, and they become neutrons, and you're left with a ball of neutrons. And this results in a massive explosion called a supernova explosion. Exactly how the explosion occurs is still unanswered. There's some good ideas about how it happens, but it's still not something that we know 100%. There's a good website, chandra.harvard.edu, that's got some good resources for looking at supernova and so on. So here's the site. There's a little introductory video that you can play here, but there's a lot of good resources, animations about different supernova and what we call supernova remnants, things that are left behind after the supernova. But it discusses a lot about how supernovas occur, what our current understanding about them is, how this Chandra X-ray telescope works, and how it's detected these things. So it's a nice website to explore. We'll talk about black holes here in a little bit, and talk about where they came from. So a useful website to look at. So the supernova explosion occurs when the electron degeneracy pressure is overcome by gravity. The core contracts suddenly. It's as if you imagine taking, like in a swimming pool, if you're under the water in a swimming pool, you've got all this water around you, but you have like a balloon under the water. And you suddenly, under the water, you pop the balloon. Well, all that water is going to come rushing into where that balloon was, where it occupied, where the space that it occupied. It's all going to come rushing in, and then it's going to kind of hit and sort of bounce off, and as it kind of comes in and hits, it sends like a shock wave back outward. That shock wave is the supernova explosion. And so during that collapse of the iron core, there's a bunch of protons that combine with electrons, creating neutrons, and neutrinos are released. So neutrinos are released, and what we're left with is this ball of neutrons that we ultimately call a neutron star. And this explosion, this sort of this sort of shock wave that's sent back outward, the supernova explosion, tears apart the rest of the star. All you have left is this ball in the center of pure neutron material. It's called a neutron star. And ultimately, it's supported by neutron degeneracy pressure, this quantum mechanical thing that says that neutrons don't want to get squished together too tightly. The core shrinks from being about the size of the Earth when it's an iron core to being about 10 kilometers across. So it's something about the size of the Earth, a ball of iron about the size of the Earth, incredibly massive, that gets squeezed so tightly that it fits into the size of a small city, about 10 kilometers across. It's incredibly dense material, incredibly dense material. If the gravity of the star is strong enough, then that neutron star, the neutron degeneracy pressure, can be overcome as well. And that ball of neutrons can be squished to almost zero, to pretty much zero size, to what we call a singularity, and that's when we get a black hole. So if the mass of the star is strong enough, gravity can squeeze that neutron star strong enough during this collapse. It all happens very quickly in a fraction, tiny fraction of a second. So you don't really get a neutron star. The collapse just continues to almost to nothing, and everything is compressed to a point. And that's your black hole. And we'll talk more about black holes in the next chapter. But in this process of the supernova exploding, more stuff can get produced, more elements can be made. All that energy and all those neutrons that are released and so on in this process, remember you have these fusing shells of material above the core. That fusion is still happening, and there's a lot of particles there that can then collide with each other during this supernova explosion. So much heavier elements can be produced, like gold and uranium. In fact, all these different things could possibly be produced in those supernova explosions as things collide with each other. And so gold is definitely produced. It's not produced in the core of stars. We can only go up to iron. All these other things are not produced during the regular lifetime of a star, but rather during the supernova explosion of a star. So supernova remnants, what is left behind? Here's a picture of the Crab Nebula, which, if you measure the speed of the gases moving away from some center point, you kind of track it backwards in time, you find that it must have exploded around 1100 AD. And in fact, if you look at Chinese records, they do talk about a new star in the sky in the year 1054 AD. So this is the Crab Nebula that was seen by ancient Chinese astronomers in 1054 AD. Energy released in this explosion, in a supernova, and sort of a typical supernova explosion, can be about 100 times more than what our sun produces in its entire 10 billion year lifetime. An incredible amount of energy that can produce an incredible number of new particles, new nuclei. The supernova 1987A, we saw it in 1987, the first one in 1987. That's why the letter A is there. And astronomers saw it with their naked eye. It was so bright you didn't need a telescope to see it, just like the 1054 supernova. And so so they were able to study it. They had the modern technology, the telescopes, and so on, to study it very carefully. And so they learned a lot about how supernovas work by studying this supernova. It was the closest supernova in terms of distance from Earth in the last 4 centuries. Measurements from neutrino detectors. So we have neutrino detectors underground in these deep underground mines, and we can detect neutrinos coming from the sun, and that confirms our understanding of what's going on inside the sun. But when this supernova occurred, the neutrino detectors were triggered, and they detected a flux of neutrinos coming from this location, indicating that most likely our understanding of what's going on inside this during the core collapse was correct, that the electrons and protons were squished together, forming neutrons and neutrinos. A huge flux of neutrinos was emitted by this collapsing core of this supernova. So what have we learned in this section? Well, high mass stars and intermediate mass stars live their lives initially on the main sequence, similar to low mass stars. But when they die, the intermediate mass stars just form carbon balls and planetary nebula. The very high mass stars can produce all kinds of different elements, and they could end up with giving off a supernova explosion and leaving behind a ball of neutrons. Or if there's enough mass, they could collapse that ball of neutrons into a black hole. And again, a supernova is a result of that as well. So in the next section, we'll talk a little bit about when stars are dying and they are in a binary system. what can happen there? If stars are kind of orbiting each other, is there any interesting things that could happen there? And then we'll go on in the next chapters to talk about these remnants, the neutron stars, the white dwarfs, and the black holes.